whether because you are making a wellbore or making a hydraulic fracture, depleting the reservoir, or injecting a fluid in the reservoir, that's going to result in different paths. For example, if the element were to be close to a fracture tip, probably your state of stress or your stress path is going to go into this direction. If your element was close to a wellbore and it's close to shear failure because of breakouts in the wellbore, probably it's going to go this way. If you are injecting a fluid into this formation because, for example, you want to push oil, or because, say, you want to sequester carbon dioxide for geological storage, which thing do you think the stress is going to go? This way? This way? So when you inject fluids into a formation, you may be increasing the pore pressure, and if the pore pressure increases and the total stress, at least the vertical stress, remains constant, what do you think will happen to the effective vertical stress?
I know Mohr's circle moved to the left.
Okay, so exactly the same as the Mohr circle moving to the left, this point is going to go on a trajectory also to the left. So this is going to be, for example, the process of injection. And on the contrary, if you deplete the reservoir, in which direction this is going to go?
Compaction, going to the right.
It will go to the right, and it will tend to go into this direction. And we're going to see later on that these plots are very useful, because here we can also add one more variable to the problem, which is something which is called a compression yield cap. And this limit is going to tell us the maximum level of compression that we can put on a rock before it starts to show pore collapse. So that's something that you have to measure in the laboratory, but what this study is telling me is that if I go from here to somewhere over here, I'm fine. The porosity is not going to change a lot. But if I cross this line, I'm going to start to develop significant compaction and pore collapse, because the rock is approaching its limit of strength under compression. It's not shear, it's compression. And in the same way, there's going to be one more line somewhere over here that also can tell you what is the limit of the rock for tension. So this type of simplification of the state of stress is going to be very useful. And that's something that I like that you become familiar with, because we're going to use it a lot later. Yes, Jack, you have a question?
Can you repeat again what if you go above the compression yield cap?
If you go above the compression yield cap, your rock will start to compress a lot more in compression, because before the compression yield cap, your pores get smaller, but more or less elastically. When you pass that, the grains start to crash, and your pores start to get a lot smaller, but because everything is collapsing around the pore. I have one image that probably is going to help see that. And until I find that, Rodrigo, you have a question?
Yes, so P it would be more or less like the center of the Mohr circle, right?
Yes.
And so if you're injecting and shifting the Mohr circle towards to the left,
Yes.
I would expect to see the stress path going just to the left also, not gaining any shear.
Okay.
But I don't know if I'm getting it wrong.
No, I think you're going into a good topic there. So let me show this image and then we'll go to yours. Let's see, for collapse. All right, so this is what happens. When you go above a given stress, your pores that probably before were nice pores, more or less of the size of your grains, after you reach a given stress, the grains start to break and occupy the pores that before were filled with the fluid. And now there is a filled with grain. Porosity decreases a lot at that point. Usually, what you will see is that you may have a rock which is more or less stiff. When you start pore collapse, it becomes less stiff because you're breaking the grains. And after you feel all that porosity with grains again, it becomes stiff again. Now really stiff.
So does that mean that it's more likely to create a fault?
No, it's in order to create a fault, and sometimes it's actually observed too. Some people claim that with depletion you can cause faults. Your stress path, instead of going this way, it has to go this way. What you can cause sometimes if you go this way, have significant shear, is what I call shear bands, compaction bands that are not specifically faults, but as you get closer into this direction, you start to have more impact on shear. So this is pure stress, pure compression, this is pure shear. So going to your point, Rodrigo, it's the direction of this. If it goes in this way, or it goes in this way, or sometimes it even can go in the opposite direction of this. It depends also on the boundary conditions. So it gets a little bit more difficult, that problem. In an infinitely long reservoir, it will go this way. That would be the analytical solution. All right, so let's see where we are. We talk about P, we talk about Q. Let's talk now about the Mohr circle again and how we make that case general for 3 dimensions. So I don't know you guys, but I didn't like the Mohr circle much when I was in school, because to me at that time they made it too difficult with these projections and you know the convention, if you go this way and that way, and it was always difficult to remember. So here I hope that I make it simpler for you and that you remember this forever, and then you become friends with the Mohr circle as I have become in the last 10 years. Again, first thing about the Mohr circle, always start by plotting the principal stresses, which we're going to do it in 2 dimensions again, just to make it simpler for now. Let's say I have sigma 1 and I have sigma 2. Those are the 2 values that you have to start plotting. And you join those 2 points with the circle or a half circle with the center somewhere over there, and that's the Mohr circle. That's it. The next step now is to interpret what that Mohr circle is. But you'll see that that's not too difficult either. I'm very picky about drawing circles. So just give me one more time. Right, that looks lovely. Okay. So we have principal stresses, we have Mohr circle. Let's see what this Mohr circle means physically. And in order to do that, we're going to draw an element with sigma 1 in this direction and sigma 2 applied on this plane. We're going to have the same on the opposite faces. This value sigma 1 is the normal stress on this face. And according to this condition, the shear stress on this face should be 0, right? But this point is that face. And I have sigma n equal to sigma 1, tau equal to 0. This other point over here is this face over here. Well, I could have picked this one and that one. It's exactly the same, okay? It is that face. All right. So, what all these points are that make a circle are all the state of the stresses going from this face, that would be sigma 1, going to sigma 2. So if I go and amount let's say theta from here to there, going from the plane of sigma 1 to the plane of sigma 2, in the Mohr circle, that's going to be equivalent to going and amount 2 theta. So, for example, when theta is equal to 90, and I get to the face sigma 2, so I go from 0 to 90, it's the same as going here from 0 to 180. And therefore, everything in between is what I have going from here to there, from 0 to 90. And if I want to compute what those values of sigma n and tau are, it's very easy, just trigonometry. This is the center of the circle. This is the radius of the circle. So at a given location, sigma n is going to be the center of the circle plus the radius of the circle times, what should I multiply this? If I want to get this distance, it's going to be the cosine of 2 theta, right? And that's it. And tau is going to be just r times the sine of 2 theta. Again, where C is equal to sigma 1 plus sigma 2 divided by 2, and R is equal to sigma 1 minus sigma 2 divided by 2. So with these two equations, I can tell at any angle what is going to be the resulting normal stress and shear stress on that particular plane at, let me extend this a little more, at a particular angle theta. Question here, where do I have the highest value of shear?
Parallel to the surface?
Yes, let me rephrase this to be more specific. At what angle theta
Oh, 40.
do I have?
45.
At 45. And that's an important value, an important location, because here I have the highest shear. But we're going to see that in rocks, it's not about the maximum value of shear by itself. What is going to be important is going to be the maximum value of shear stress divided normal stress. In, for example, uncemented surfaces, I would like to compare this to the friction coefficient. I know that if the shear stress is higher than the friction coefficient times the normal stress, that surface is going to slide, which is equivalent to shear yield or shear failure. If this amount is less than the friction coefficient times the normal stress, that surface or that fracture will not slide. All right, so this is the case for 2 dimensions, and it's very simple. Let's see now how this works in 3 dimensions, which is a little bit more complicated. And here we go. So this stress decomposition sometimes is also called stress projection on a